we had written down 3 kinematic equations to describe motion of an object. Now that was motion along a straight line path. We're going to be dealing with more complicated motion now. We're going to be dealing with rotational motion. But it turns out the equations are exactly the same. So everything along a straight line path has an analog. Every quantity has an analog between angular world and straight line world. So what we can say, let's erase this. What we can say is that what I used to call position, that's where position told me where I am. Well, now we're going to change from position to an angle. The angle is going to tell me where I am. It'll tell me where I am, how far I've rotated around. And it will be true for all different types of positions. So just like I had an initial position before, I'm going to have an initial angle now. Just like I had a final position before, I now have a final angle. Just like I had a displacement before, I'm going to have an angular displacement. So position has its own version in angle. Just like we had velocity, we are now going to have angular velocity. So velocity is going to get turned into angular velocity, which gets this Greek letter omega as a symbol. And much like velocity was the change in position over the change in time, angular velocity is going to be my change in angle over my change in time. So how much does my angle change per unit time? So if I go 90 degrees, or equivalently half pi radians, what that would mean, let's say I did that in 1 second, so that would be 90 degrees per second, or equivalently pi over 2 inverse seconds for my angular velocity. All it's telling me is how many angles I go per second, 90 degrees per second. Just like we had meters per second before. Now we're just in angle. We could also accelerate. Our rotations can accelerate. So if I start rotating slowly and then speed up, I have some angular acceleration. Instead of acceleration, we call that angular acceleration. And instead of the letter A, we get the Greek symbol alpha. So what we find is that going from linear motion to rotational motion, we're going from English letters to Greek letters. We started to run out of variables. But my angular acceleration is just the same formula with the variables replaced by the Greek variables. So acceleration was the change in velocity divided by the change in the time. Angular acceleration is the change in the angular velocity divided by the change in the time. It's the same thing, it's just we're switching over all of my variables that I used to have for regular linear motion are now switched over, and we're using their angular versions. So we can describe the rotation of objects using kinematic equations that look very similar to the kinematic equations we had for the regular linear quantities. The only difference is that we're going to be replacing them by their angular versions. And it's going to work very similar to the way it did before. So before, we had motion, and that motion could speed up or could slow down. Okay, well, angular rotation is the same thing. We can speed up our angular rotation, or we could slow it down. Let's see how those equations describe those changes in motion. So before, we had 3 kinematic equations. One of them described your position as a function of time. Now it's going to describe your angle as a function of time. So our first equation will look like this. So we would say that our final angle is equal to our initial angle plus our initial angular velocity times time, plus 1/2 the angular acceleration times time squared. It's the exact same equation that we wrote down for kinematics. I've just rewritten the variables using different letters, Greek letters, to describe the angular versions of the quantity. The next equation I wrote down was in terms of the angular velocity, or excuse me, I wrote it down originally in terms of the linear velocity. Now we're going to write it down in terms of the angular velocity. So we would say that our final angular velocity was equal to our initial angular velocity plus angular acceleration times time. Again, it's the same exact equation we had before. The only difference is that I've replaced it with the angular versions of the quantities. The equations work exactly the same both ways. Now, there's one more equation. We wrote this one as the difference between the squares of the velocities. Now we're going to write it as the difference between the squares of the angular velocities. So omega final squared minus omega initial squared equals 2 times the acceleration, now the angular acceleration, times the displacement, but now times the angular displacement. So these three equations can describe any type of motion that involves constant angular acceleration. Suppose we want to know about the motion of one particle in our rotating object. So say I want to plot the motion of my little green dot that's spinning around here. Let's say I want to know where it is, I want to know how fast it's going, and I want to know its acceleration. And I want to know the linear versions of these quantities, not the angular versions. Well, we can describe the regular old position, velocity, and acceleration by converting from the angular properties. And it turns out it's fairly easy to do. So if I want to know how far I've traveled, where I am on the circle, we've already talked about how we can measure that as an arc length. So my arc length is just equal to theta times the radius. Now it turns out that both the acceleration and the velocity, at least the acceleration and velocity along the length of the circle, tangential to the circle, can be described pretty easily just by multiplying by r. So if I want the tangential velocity, I'll call it vt for tangential. By tangential, I just mean it's the velocity along the tangent to the circle, so along the surface of the circle. Along the edge of the circle, I should say. My tangential velocity is just going to equal my angular velocity times the radius. And if I want to know my tangential acceleration, how much I'm accelerating along the edge of the circle, again, it's just going to be written by the angular quantity, in this case the angular acceleration, times the radius.